Today I will talk about decomposition of time series. Time series have following components: trend component, seasonal component, cycling pattern, and residual component. This is the multiplicative model of time series, where time series is equal to multiplication of trend component, seasonal component, cyclic pattern, and residual component. This blue one is actual time series original data, and we can see that this is a trend component which is increasing. This is a linear trend. This is a seasonal component, and then this is the cyclic plus residual component. Let us see how to calculate the trend component. This is our data. These are years and these are quarters. So this is first quarter of 1999. This is second quarter of 1999. This is third quarter of 1999. This is fourth quarter of 1999, and this is first quarter of year 2000. So the quarter previous to first quarter of 2000 is quarter 4 of 1999. For calculations of trend component, first we need to calculate the yearly average. These are the yearly averages, and this is the total. The last row represent total. So this is, we are subtracting the mid-year from rest of the years. So for the year 2001, this t minus 2001 is 0. And for previous years, it is -1, -2. And for successive years, it is 1 and 2. And this is the total. This is the square of this column. And this is the multiplication of yearly average and the t value. So, and this is the total. So by solving the equation of linear regressions, or by using the analysis tool pack in Excel, we can calculate, or we can identify the linear regression equation. And the equation for this data is 63.25 plus 4.48 multiplied by time stamp. So this is the intercept 63.25. This is the slope 4.48. So every year there is an increase of 4.48 according to this linear regression equation. So we can, therefore, using the linear regression equation, we can calculate the trend values for the year 1999, year 2000, year 2001, year 2002, and year 2003. So these are the trend values for each year. Then, since this is the increment per year, this is the quarterly increment, that is 4.48 divided by 4, that is 1.12, and this is half quarterly increment. So using this yearly increment and quarterly increment and half quarterly increment, we can calculate the trend values for all the quarters. So if we take the yearly trend as a mid value for previous quarter, we subtract half quarterly value, and for this quarter, we subtract from this 1 quarter value. So these are the trend values. So this is how we calculate the trend values. Now we come to seasonal component. This is the original data. For the seasonal component analysis, we first need to calculate the link relative, then chain relative, then K and D values, then adjusted chain relative, and then seasonal indices. Finally, we need seasonal indices. So let us see one by one each one of these. So this is original data. Link relative is equal to season's value divided by previous season's value multiplied by 100. So for this season, that is quarter 2, the link relative is 54 divided by 45 multiplied by 100. So this comes out to be 120. Similarly, for quarter 3, this is 133.33. It means that in quarter 3, in the year 1999, there is 133.33% increase as compared to quarter 2. And in quarter four, there is 83.33% decrease as compared to quarter three. So these are the link relatives. And for this quarter one of year 2002, the previous quarter is quarter four of 1999. This is very important. Then chain relative is equal to average link relative multiplied by previous season's chain relative divided by 100. So in this scenario, for quarter one of 1999, uh, first of all, for quarter one of every year, we calculate the average link relative. For quarter two of every year, we calculate the average link relative. So we have average link relative of all the seasons or all the quarters. So the chain relative, first chain relative is taken as 100. Let us say that chain relative 1 is equal to 100. And the next chain relative is the average link relative, that is 121.38, multiplied by previous season's chain relative and divided by 100. So this comes out to be 121.38, and so on. We can calculate the chain relative of all the seasons. These are the formulae for K and D, and this is the implementation of formulae for our present data. And so the adjusted chain relative is equal to chain relative of a season n. We have divided quarter 1, 2, 3, 4 as season 1, season 2, season 3, and season 4. So n represents 1, 2, 3, 4, and this is the formula for adjusted chain relative. So the adjusted chain relative comes up to be these four values, and the average of these four is 120.78. Now the seasonal index is equal to adjusted chain relative divided by average adjusted chain relative multiplied by 100. So this was the average adjusted chain relative, that is 120.78. So the seasonal index for quarter one is 0.83, for quarter two 0.98, and so on. So this was our desired output. These are the seasonal indices or seasonal component. And on a visually looking at the data, we can say that most of the sales happened in quarter three. It was maximum 1.15 seasonal index, followed by quarter four, and the minimum was quarter one. So this was about seasonal component. Then cyclic component. Cyclic component can be easily arrived by using the multiplicative model. This is our original data. These are the trend values. These are the seasonal indices. And if we divide original data by multiplication of trend values and seasonal indices, we can arrive at the cyclic plus residual component. So this is the cyclic plus residual component. So this is the entire data from year 1999 to year 2003. This additional column I have inserted so that we can make graph using Excel. This was our original data. These are the trend values. Trend is increasing. This is the seasonal indices or seasonal component. So it is repeating after every four values. Then this is our cyclic plus residual component, and we can plot it using Excel. So this is the plot as we have seen initially. This is the plot of our this data. This is the original data. This is the trend component. This is the seasonal component, and this is the cyclic plus residual component. So now let us see how we can quickly do the calculations using Python codes. So time series decomposition using Python codes. These are the basic libraries or packages which we need for general purpose: NumPy, Pandas, and Matplot library for plotting. This is to set the figure size as a smaller size. This is the code to import the data. This is our file name, and we need to set the column month as index column, and this is the head of our data. This is the index now, and this is our data. This is the same data which I have shown you previously. and we will do the calculations on the same data. So this is the plot of time series data. So this is how it is increasing, and it has these components. This is code for decomposition. It is very simple. This is the package, and this is the code for decomposition, and this is the code for plotting the graph. So this is our decomposition using Python. This is the original data. This is the trend which is increasing. This is the seasonal component, and this is the residual component. This is comparison of the manual calculations and automatic calculations using Python codes. The difference is that in our manual calculations, we assume linear trend, and here the trend is not linear. So there is slight differences in these further graphs. Otherwise, the results are very much similar. This is the end of my lecture. Thank you very much.